As I promised you last time then, this week we're going to be taking a slightly deeper look into how Plink Parallel Link works. And let's just recap what we were looking at last time. So, tidied it up a bit, but basically we had this application where we created 500 million numbers starting at 0, going up to 499,999,999, and then we had a link query, so we did values as parallel, so that's what gives us the plink, the parallel link, and then we had this factorial where I just did a bit of work to keep the numbers in a sensible range so the factorials didn't get too big, and so we do the factorial of each one and then we average it. And I've also got this count which basically allows us to keep track of, on that factorial, which thread was being used how many times. And so if we just run that up, then what we'll see is, if we just look in the diagnostics tools, there we're using a nice big chunk, almost 100% of the processing power, so it goes nice and quickly. I'm on a 16 core machine here and we've used all 16 cores, and you can see there we've got 16 threads, each being used roughly the same number of times, and then that figure is the average that we had. So that's where we've done it last time, but let's have a look in a bit more depth at what we've got there. So let's actually break this down a little bit, because I've said that values.asParallel is what does all the work. So let's actually take that out and we'll just do a var parallel equals, and then have that, and then in here we can put our parallel. So that just breaks it down a little bit. But the thing we can immediately notice here is if we hover over that parallel, the type of it is parallel query generic for int. So if I just had this as values, that was simply an IEnumeral int. But this is a feature that you quite often get with Link, that when you do a certain operation like as parallel, you get back actually a different interface. So you're probably familiar with the fact that with Link, sometimes we're using iQueryable, sometimes we're using IEnumerable. We also, if you do an ordering operation, have another interface for that, iOrdered enumerable, and here we've got this parallel query, which is what gets returned from as parallel. And because Link fundamentally works using extension methods, and extension methods bind statically to the type, the interface or the parallel query class we've got here, then that means that we're actually going to get a whole different set of methods when we make calls. So that average, although it looks exactly the same as the average that we get with IEnumerable that we had before, it's actually a different method, a different extension method, and that's how we can get completely different behavior when we've got the parallel query, even though it's the same basic data. So that's what we have there to give us our parallelized query. And then once we've got that, that means as well as having different implementations for some methods, we can also have some brand new methods. So if I go for parallel dot, then a lot of this is the same sort of thing you'd be used to, but if we just go in here, you can see we've got a number of these with methods that gives a way of just tweaking the way that the parallelization is going to work. And so one of the really easy ones, we've got this with degree of parallelism. And what that allows us to do is specify the maximum number of cores that are actually going to be used in the query. Something to watch out for here, if I just do that on the existing parallel object, that's not going to have any effect because it's going to be returning a different object with that degree of parallelism. So actually, I have to put that on there. I'll also just reduce that number because this is going to take a bit longer. But now, if we run that up, then what we'll notice is it's down to 13% of the processing power. You can see that when we have keeping track of our cores, it's only used 2 of them because that's what we told it to do. Now, obviously, having that hard-coded may not be a brilliant idea, but another thing you can do actually is in here, you can use environment.processAccount to tell you how many cores are actually available on the target machine you're running on, and then we could just say only use half of them. So now, if we run that one up, it's used 8 of the 16 cores, so it's used half of them. And that's not something you'd absolutely be hard coding into your application, but it might be a configuration option for your users because it's them that's going to decide how much of their processor your application is going to be using up. So that's just one of the features we've got there. We've got some other ones as well that I won't go into too much depth. We've got things like with cancellation, if you want to have a cancellation token, with execution mode that can force it to actually always do things in parallel, even if it thinks there may be better ways, some other things like that. So those are some of the options that we've got. Now, one thing to watch out for is that when we do our parallelized calculation, the actual order that the individual cores will do their bits of the work in is going to be effectively random. So if we just simplify this a bit, let's use smaller numbers now just so we can keep track of things. And then in here, all I'm going to do is actually select, and then let's select val times val. So all we're going to do is square the numbers, and this time, rather than doing an average, we're actually going to get back a sequence. So let's call that. Now we can get rid of that lot. And then, typical way you'd then look at a sequence is you'd say for each, and then var I in sequence, and then we'll just console write the value of I. So that should print out our sequence of squares. Won't take very long because we've only got 1 to 10 in there, but if we run that up, then the thing we notice is that sequence is coming out in this random order. Because what it'll actually have done here is probably split this into 10 completely separate cores, so each one is only doing one bit of the calculation. They get to do their job in this effectively random order, and then deliberately, when the data is merged back together into the final sequence, there is no effort made to preserve the original order. Okay, so that's why we get it out randomly. And that's done deliberately because that's going to be the most efficient thing to do, not wasting time making sure the numbers come out in the same order that they went in. And in many cases, that's not going to matter at all. For example, when we're doing an average, then it doesn't matter what order you average a set of numbers in, you're still going to get the same value. Whereas here, when we're printing that sequentially, obviously that can make a difference. So one thing that we can do is actually on this as parallel, we can do as ordered. There's also, to reverse it, if you later on you want to do as unordered, but if we do an as ordered on there, then that will now, although it still processes the threads in effectively a random order, once it's processed them all, when it recombines things back into the final sequence, it will preserve the original order. So if we run that one up, then we can see that we're getting the squares in the order that we expected them. Another thing we can do, I've popped in a little function here called flag, and all that's going to do is tell us what number we're processing and tell us what thread it was on. And so if I take that square and wrap it in this flag, then what we'll also see is the order it's processing them is still random. So it's not stopped the randomization there. They're happening almost exactly at the same time. That's why it's effectively random. But then the results come out in the sequential order. Nothing to point out about this as ordered. It's not doing anything like sorting. It's not like an order by in the LINQ query, in that it is not trying to put them in ascending or descending order. If I were just to replace that with a fixed array, so an array of ints, and let's put in 5, 2, 3, 6, and then if we run that, we'll see it's 25, 4, 9, 36. So it's not tried to sort them numerically, it's just preserving the order that they went in with. That's the order that they come out with. And sometimes that's going to be necessary to do, that you want the sequence to come back out in the same order. If so, you can use the as ordered, but bear in mind there is some overhead with that. Exactly what it's going to be is obviously going to depend on circumstances. You might want to do some measurement and benchmarking, but that's something you need to be aware of. So that's what we have with as ordered. Now actually, another thing we can look at is the fact that for each may not be the best thing to do for all of this calculation. Again, really for reasons of performance. Because we have an alternative when we're dealing with Plink, and that is we can use a thing called for all. And that is actually another extension method that we have on the Plink object. So if I go for sequence dot, then you can see we've got this thing called for all. And what for all does, it will take a lambda expression that gives you the particular value we're dealing with. So this is going to give us those squares. And then we can put in some code that then processes them how we want. So what we could do here is a right line. And then what we'll do here is we will just put in displaying and then val and then on. And then we're just going to show what thread we're on. So current managed thread ID there, just so we can keep track of what's going on. And what we can see there is if we run that up, that those are being intermingled. So where it says processing, then it is in this square bit where the processing is coming from the flag, whereas when it says displaying, it's in the for all. And you can see it's not waiting to have finished. So as soon as one of the parallelized threads has finished doing the square, it can move on and do the for all. And you should notice that the numbers are the same. So when we're processing 49 and displaying 49, that was on thread 11. When we're processing 36 and displaying 36, that was on thread 12. So what this means is we can do our display still in parallel, whereas the for each is definitely going to be non-parallelized, so that is always going to be on the main thread. And so if we do this, what you'll notice is that although the processing and the displaying are intermingled, the final display, because it has to be done in the main thread, is all going in one thing on the end. And also another thing to notice, although the end results are ordered because we had the as ordered, the intermediate stuff that we're getting on the for all is pretty much randomized because that is just processing each one as and when it's ready. So we can see slight differences there. For each is going to wait until everything's done, so it's not going to start reporting immediately. But if you've gone for as ordered, it will do it in the correct sequence. For all can start displaying much quicker, and it's going to be doing it in a multi-threaded way. But because of that, it doesn't yet know the order because we haven't reassembled the sequence on the end. So both have their uses. Generally, for all is going to be more efficient, but clearly if you want the sequence in a particular order, then you're going to have to wait till you've finished and use the as order. Now, some other things we can do, as we mentioned, is we can use some of these extension methods like average. So if I just take that whole query and put average on the end, and probably best to rename that to average, get rid of these two for now, and then we can just do a console write line of average. Then obviously what we've seen is that we get an average there of the average of the squares of 38.5. And worth bearing in mind there that actually the ordering doesn't matter. When you calculate the average, the ordering doesn't matter, so it doesn't really matter whether we had as ordered in there or not. The way average works, obviously you do the sum and then you take that sum and you divide by the count. So if we want to change that again, if I just do the sum, we can put the sum in there and sum in there, and that will give us the sum of our squares that we've got in there, 385. And the way it does that is it basically takes the sequence of numbers, chops them up into however many groups we have for our number of cores, and then works out the sum on each of those chunks. So on a 16-core machine, there'll be 16 of those chunks. And then finally, it's just got to add together the results from each one of those 16 chunks to produce the final sum. And that approach will work with lots of these methods. So it will work with sum, it will work with max or min. So you break it up into 16 chunks, you work out the max for each chunk, that gives you 16 results, you work out the max of those 16, it's the same as giving you the maximum of the whole collection in one go. So that's how these things can manage to break it down, and there's no real issue of having data crossing between the threads because it's only that very last bit, which is going to be a very small calculation, adding up your 16 numbers, that requires any kind of collaboration between the threads at all. And in fact, that whole idea can be more generalized into a function that we have called aggregate. So what I can do is similar sort of things for myself that aren't just sum or max or min, but whatever rule I want to have. And so the way that aggregate works is like this. What I could do is I could put in a lambda and we'll have one parameter as sum and another parameter as next. And then in the body of that lambda, I could simply do a return sum plus next. And so basically that will put together the sum. We can actually keep track of what's going on here. So let's do a console write line in there and we'll say sum dash next on, and then let's once again show what thread we're working on. And in fact, to simplify matters, let's not do the square. So let's just select the val, and also let's not even make this parallel as yet. And we should see when we run that we're getting what we'd expect. So it takes the first two numbers, 1 and 2, adds them up, gives us 3, then it takes 3 and 3, adds them up, gives us 6, then it takes 6 and 4, adds them up, gives us 10, and so on and so forth. And so the sum of the numbers 1 to 10 is going to be 55. And you can also see, because I didn't parallelize that, that's all running on thread number 1. Whereas if I put that parallel back in, then we can see that it's now got that randomization again. So we're starting out with some very strange sets of numbers, but it's still producing the same result because all the numbers come through. When you're doing a sum, it doesn't really matter how the things have been mixed together. And so that's perfectly okay. But now let's do something a bit different, because the thing about sum, and in fact most of these aggregate style functions we're talking about, is they are what is known as commutative. That's to say, as we've seen here, it doesn't matter what order the numbers are processed in. When you add up a load of numbers, you still get the same result regardless of order. But what we can do is we could have a slightly different calculation. So let's change that. This isn't a particularly meaningful calculation, but it will show us the problem that we have here. So if we return 2 times sum plus next, now let's firstly do that without parallelization. And so if we run that, then we'll see that obviously they're going forward all on the same thread in the order you'd expect, and we get a result of 2036. And you can work that out for yourself. That's the correct number. We should get the same results every time. But that is now not going to be a commutative function. The order is now going to matter. And so if I put as parallel on here now, and we run it up, we can see now we're getting the randomized order of processing, but that also means that we don't get a consistent result, because it's now going to depend on what order things have gone through. So that time we got 962, this time we get 792, this time we get 2, 3, 4, 5. So clearly that is not a very good idea to parallelize something for an aggregate function like this where the order is going to matter. And so it would be a better idea just to leave this one as sequential. There's no way really you can take advantage in terms of performance of parallelization if each step of your process has to be done after the previous step has been done. There's no opportunity for parallelization, so we might as well just do it in a non-parallel way. But having said that, what if we're actually doing something a bit more like we had before? What if we were trying to do a square and then do this calculation, this aggregate, on the squares? So if we run that, we can see the answer to that one is now 5998. Still going to be consistent. But the problem now is, in terms of efficiency, we know this bit has to be run sequentially, but this bit would be perfectly good to run in parallel because there's no interaction between the different bits and pieces. So what we'd like to do is have the best of both worlds. And we can do that because if here we say dot as parallel, so that means it's going to start doing things in parallel. So the next bit of work it hits is going to be the squares it'll do in parallel. And let's actually put our flag back on there so we can see what thread they're being processed in. And then what we can do is, after that, before we do the aggregate, we can do as sequential. So as sequential is the opposite of as parallel. As parallel tells Link that it's got to do this in parallel. As sequential tells it to stop doing it in parallel, do it back in a single thread. And so if we run that, what we can now see is here we've got the processing in a random order. So you can see those are random and happening on lots and lots of threads. And then here, well, this is getting a bit odd. It clearly is sequential because we're getting thread 1 for each case, but it's still coming through in a random order. So we've got 181, we've got 281.4. It's not the order we wanted. And that's because actually we've got to do two things, because all the as sequential does is tell it to start processing on a single thread. But the sequence that's coming out of the parallel bit, remember, is not going to be ordered. By default, it's not ordered. So what we have to remember to do is as well as using as sequential to get us back on the single thread, we've got to do the as ordered so that the results coming out of that are reassembled into the correct order, so we'll then get them running okay. So in that case, we should now see that this processing is happening randomly and on multiple threads, but this processing is happening in sequence and on the main thread as well. So we're there getting the best of both worlds. So a few complexities we've got there, but certainly some quite powerful things that you can do. We can decide using for each or for all whether we're going to wait till all the processing's finished and then just do our last bit on the main thread, which is for each, or with for all we can do some additional processing still within the multi-core approach and carrying on from whatever the earlier processing was done in. And then we've also seen we can have things like aggregate, which are similar to average and max and min and sum. And if you've got a commutative operation, it's up to you to work out, certainly with aggregate, whether what you're doing is commutative, is independent of order. Well, if it is independent of order, that's fine. You can just do it in parallel. But if it's order dependent like we have here, you're going to have to use either you're going to have to just not parallelize it at all, or in a situation like this where we've got the square that can be done in parallel and the aggregate that can't, then we switch between them with as ordered and as sequential and as parallel. So quite a lot of subtle things we can use there, but it really does mean we can get the best out of our processor and make our code run as powerfully and as quickly as possible. So hope you enjoyed that. If you did, do click like, do subscribe, and I'll see you next time.